In this video, we're going to begin to look at the use of the Monte Carlo method to estimate in a statistical manner various values that we wish to calculate. These can often be thought of as being integrals, and as a first example we're going to use random numbers to calculate the value of pi, which is a classic example of a Monte Carlo calculation. Now, random numbers we'll look at in a bit more detail in a following video, but in many operating systems or programming languages or environments, there are functions that will return what are called random numbers. These are actually, for the most part, so-called pseudo-random numbers, which we will define better later on. In MATLAB, the random number function is called rand. So if I call the rand function without an argument, I obtain a number, and if you see by repeatedly calculating the result of that function, you see that a set of different numbers are generated, and these numbers are distributed uniformly, as it's called, between 0 and 1. Now, interestingly, if you were to load MATLAB again, if you were to close down MATLAB and reload it and run this rand function again, you will actually get the same sequence of numbers appearing. These numbers are pseudo-random numbers, which means that they are actually related to each other. Each successive value is uniquely defined by the previous value. Of course, they're not displayed with the full accuracy with which MATLAB is calculating them, but this sequence of numbers is repeatable, and one can select which is the first number by selecting a so-called seed. So again, we'll look at that in a bit more detail later. Now, MATLAB, being matrix laboratory, means that if I call the rand function with a single argument 3, I obtain a 3 by 3 array or matrix. So in order to obtain a list of random numbers, I would need to use the following argument. I need to give it either 1, 100, or alternatively 100, 1, and in both those cases I obtain a list of random numbers which is 100 elements long. Now, how are we going to calculate the value of pi? Well, imagine if I have a circle of radius 1, and this is inscribed inside a square which has side length 2. So the square runs from -1 to 1 in x and from -1 to 1 in y. Now, if I consider the top right quadrant of that picture, I have 1/4 of a circle, and I have a unit square which runs from 0 to 1 in x and 0 to 1 in y. Now, the area of the full circle is obviously pi r squared, where r equals 1. So its area is pi, which means that the area of the top right quadrant is pi by 4. So we can now imagine a procedure, and this is the Monte Carlo procedure. We can imagine a procedure by which we could select random numbers across that unit square, and from that obtain an estimate of pi. Let's see how that's done. I'll create a new script. And as usual, I'm going to give it a name, estimate pi using Monte Carlo. And as usual, I'm going to close any plots I had, clear any variables I had, and display all variables in long format. And I'm going to take successive values of a random number. So I'm going to generate coordinates, xy coordinates, in the unit square from 0 to 1, and I'm going to, let's call this n is the number of samples. I'm going to set that for now to be 1000, and I'm going to calculate a set of random numbers. So I'm going to do this procedure n times, and at each point I'm going to generate a value x equals rand. So this will generate a number from 0 to 1, so I've noted down in the comment. I'm going to generate a y value is equal to another random number. And remember that these numbers, I'm supposing that these numbers are uniformly distributed. This is what the definition in the random number generator in MATLAB gives us, and is what virtually all random number generators actually do. A uniform distributed number is one that has an equal probability of lying anywhere over the interval from 0 to 1. So this means that if I were to ask the question, is the the distance of this xy coordinate from the origin, if that distance is less than 1, then that value lies within the circle. And if that value lies outside that radius 1, then it's obviously outside the circle. So I can use that as a method of calculating pi. So let's see how that works. Firstly, we calculate the value r as being the square root of x squared plus y squared. So that's the distance of this point from the origin. And I now need an if statement. So I say if r is less than 1, whether it's less than or less than or equal to doesn't really matter, and we'll put an end statement below. So we wish to accumulate, we need to count how many points lie inside this circle. I'm going to call that the tally. So independently of this iterator I, I'm going to keep a tally of how many of those randomly selected points lied inside the unit circle. So my initial tally value, so I haven't had any so far at the beginning, is 0. So if I find that r is less than 1, then tally equals tally plus 1. Now there are other notations for doing that addition in other languages, of course, and in MATLAB, but we'll just do it in the most simple syntax. So that's it. All I have to do is evaluate this if statement for each and every one of these pairs of points that I calculate, and I've obtained a measure of pi. Well, how do I do that? Well, my statistical measure of pi is based on this. If I've run 1,000 trials, that's line 7, I've run 1,000 trials, and I count up how many of those randomly selected points lie inside the circle, that is a statistical estimate of pi divided by 4. So pi 4, my estimated value of it, is equal to t, the tally, divided by the total number of samples. So therefore my estimate of pi is simply equal to 4 times pi est. Okay, obviously I could have done that on a single line, but I'm just showing you explicitly how this works. So let's just save that script. I'm going to call it pi estimate, and it appears there on the left, and I'm going to run it, see how it works. Oh, undefined function pi est, pi 4 est here, there it is. Save it again and run one more time. And what do I have? I have pi est has been calculated as being 3.10. Maybe I should display that as part of the calculation. So disp pi est, save it and run it one more time, and it now comes out as being 3.2. I run it one more time, 3.18, so it appears to be working. Now obviously these points are fluctuating randomly up and down. These values of pi that I've estimated are statistical estimates. So if I wish to improve the accuracy of that estimate, I should increase the number of samples. So let's make n 10,000 instead of 1,000, and let's see if that works. And as you will see, I get a slightly better accuracy. Okay, so whilst the value of pi that's being generated from each run is varying because the different set of random variables are being obtained, on average, the variation of those estimated values of pi is over a smaller range. And it turns out that the standard deviation of those values goes as the square root, 1 over the square root of the number of trials. So if I wish to obtain about factor 3 better accuracy of my estimate, I need to have 10 times as many points, which of course takes 10 times as long. But it seems to be still calculating reasonably well. So let's put another 0 on the end. So you can see that a good way of using the Monte Carlo method is to do an approximate calculation with a small number of trials to see that things are approximately working, and then to increase the number of trials to obtain better value. Now clearly in this case we already know what the value of pi is, and there are different ways of calculating pi. There are, for example, the standard ways which are used in generating these sorts of trigonometric functions, by using some form of expansion. So there is a set of terms that can be explicitly calculated, which will give successively better estimates of pi to whatever desired accuracy we like. This method is an alternative which has a different rate of convergence for the number of terms that I use. So of course here what we've effectively done is calculated a very large number of values which have either been yielding 1 or 0, so it won't converge very fast, but it does eventually converge to give a sensible value. You can see here that already we can calculate quite readily 1 million samples in a very short amount of time. The delay between pressing the run button and getting the value back is actually quite short. So if I add 2 more zeros on, that will take 100 times longer, and it should generate values to be values more accurate by about 1 decimal place, about 10 times better. So I leave it a little bit longer and I obtain a value. So that's the basis of the Monte Carlo method. We can take samples over some range of values, and we can, by tallying up using some criterion, we can tally up those values and see what we obtain. So you can see here in this latest value, this latest estimate here, where I've used, what is this? This is 100 million, isn't it? Yeah, about 100 million samples. I obtain pi to approximately 3 to 4 decimal places.